This is the section 5.4 to 5.5 review, number 5, and calculators are not allowed. Because calculators are not allowed, this is going to be kind of a tough problem because it involves the chain rule going backwards, so that substitution method. It involves trig, and you have to do everything by hand. So you really need to know your exact values and your unit circle, in addition to knowing how to do chain rule backwards and apply the fundamental theorem of calculus. So if we look here, we see that we're given the derivative of something, and we're given a point on the original curve. So we have a point and a derivative, and I'm asking for another output. So that means I need to be able to write the original equation so that I can plug in 0. Well, the only way I'm going to get there is if I can write y at any time. I guess I'll use t's here. Y at any time is going to be the y coordinate I start with plus the accumulation from when I had it. Well, it looks like we've got x's, so I'm going to put x here instead. Up to x on our derivative function. So that'd be a secant squared t times a tangent squared t dt. So I need to figure out what the y function is before I can plug in 0. So to do that, I have to be able to answer the question, what did I take the derivative of with respect to t that gave me this inside value? So to get there, I'm going to put a little break here. I'm going to come off to the side, and I'm going to do that substitution method that we've been practicing. If we look here, we have multiple options for our u, and I'm going to tell you that the u that works best, if you remember we did a problem like this in class, the u that works best is the tangent. The reason that works the best is because the derivative of tangent is a secant squared, so the dx, when you do the substitution, is going to get rid of that, and we'll be left with a u squared, which is a power rule, and we know how to go backwards on power rules. So we can write u equals the tangent of t. So dt is going to be 1 over secant squared of t, which means if I replace my boxes, I'll have a secant squared t times a u squared times a 1 du over a secant squared of t. Notice the secant squareds cancel. And now let's think about the limits. Because I have a definite integral here, that means I can change the limits to u limits. So my u limits would be plugging this value of t in and computing what comes out. So if I plug in a pi over 4, the tangent of pi over 4 is a 1. So my lower u limit is going to be a 1. If I plug x here, then I will have the tangent of x is my upper limit of u. So if I do the antiderivative now, I will get, what did I take the derivative of with respect to u that gives me u squared? And the answer is a u cubed over 3, and I'm evaluating from 1 to tangent of x. That means I get to plug in tangent of x first, and then I plug in the 1. So this is what this definite integral is equal to. So I can now come back over here and write it down. I now have y in terms of x, and the question is, what is y of 0? So if I plug in 0, I will end up with a negative 1/3, and that's the answer that you would look for. With part B, we again need to write down the fact that we know a point on the original and we know the derivative of the original. So we can write y for any value of x will be the y we start with plus the accumulation from when we had that 3 up to x on the derivative, and I'm going to pull that negative 5 out in front since it's a constant, and I will change these to t's because we don't want to have an upper variable that is the same as what's inside. Now, in order to compute this, we are going to have to be able to evaluate the definite integral, and we can't evaluate the definite integral until we do a chain rule in reverse or a substitution method. So we have to pick an appropriate u. And I'm going to tell you that cotangent is an appropriate u because it's inside a u to the fourth, which is a power rule. That's really easy to go backwards on. And the derivative of that cotangent is a negative cosecant squared, so that's all the leftovers. Not only is it in there, but that dt, when we replace it with the du, is going to it's going to cancel out that cosine squared. So I'm going to box the cotangent and I'm going to box dt, and we will write down that u is the cotangent of t. So then we'll compute what dt is. That's a du over the derivative of this, which is a negative cosecant squared t. And then we're going to rewrite our integral so that it has just u's in it. So that would be, and I'm going to ignore the negative 5 for right now, we'll come back to that in a second. So I have a cosecant squared t times a u to the fourth times a du over a negative cosecant squared t. Notice that the cosecants will cancel, and I can pull this negative out in front, so I'll have a negative u to the fourth times a du, which is very easy to go backwards on. Now, because this was a definite integral, we want to make sure that we track the limits as we go through this process. So if t is pi over 3, then the cotangent of pi over, that's a pi over 4. That's going to be much easier to work with. Then the cotangent of that pi over 4 is going to be the reciprocal of the tangent of pi over 4. So that's the reciprocal of 1, which is just 1. So my lower limit will be 1. My upper limit will be x plugged in for t, which will give me the cotangent of x. So if I do the antiderivative of this now, I will get a negative u to the fifth over 5 evaluated from 1 to cotangent of x. I don't need to do the plus c because I have a definite integral and I can evaluate it using any antiderivative. So what I will plug in first is the cotangent, and then I will plug in the 1. So let's come back over here and do that. We have a 3 plus a negative 5 times this with the cotangent plugged in minus this with the 1 plugged in. So that'd be minus a negative 1/5. If I now distribute this negative 5 through, I'm going to get y of x equals a 3 plus, that should be a 5, not an x. The 5's will cancel, I'll get a plus a cotangent to the 5th, and then I'll have minus a 1. That simplifies to give me a 2 plus a cotangent to the 5th of x. Our goal now that we have found y of x is to talk about or compute what the output's going to be when I plug in a pi over 2. So if I plug in a pi over 2, that's going to be a 2 plus the cotangent of pi over 2 to the 5th. So let's remember that cotangent is the same as cosine over sine. And you should hopefully all remember that cosine is 0, whereas sine is a 1. So 0 over 1 is going to give me 0 to the 5th is still 0, so I'll end up with a 2.